In this video, we'll continue to look at electricity. We'll take a look at a few questions and we'll use equations that we derived so far. So let's begin. Now, question 1 says, if a charge of 180 coulombs flows through a lamp every 2 minutes, what is the electric current in the lamp? So, if a charge of 180 coulomb flows through a lamp every 2 minutes, what is the electric current in the lamp? So let's begin by writing on the information that we have using the usual symbols. So the charge Q, flowing is given as 180 coulombs, right? And we're told that this charge flows through the lamp every 2 minutes. The 2 minutes, of course, represents the time for which the charge is flowing. So the time taken, T, is equal to 2 minutes. But of course, we know the SI unit of time is the second, and so we must convert this time from minutes to seconds. Of course, 60 seconds equals 1 minute, so therefore to convert from minutes to seconds, we multiply by 60. So this gives us 2 times 60, which is equal to 120 seconds. So we're given the charge Q and the time T, and we're asked to find the current which is flowing in the lamp. And so what we want to find is the current I. So using our equation, I equals Q over T. Of course, if you recall, current is the rate of flow of charge. And from that definition, we get that I is equal to Q over T. And therefore, this gives us 180 coulombs divided by 120 seconds. This basically simplifies to give us 3 over 2, which essentially is equal to 1.5 amperes. So the electric current flowing in this lamp, of course, would be 1.5 amperes. So I mean 0, 0, 12, 6 into that, 2, 3, right? So 3 over 2 or 1.5 amperes. So this basically means that when the charge of 180 coulomb flows for 2 minutes, essentially means that a current of 1.5 amperes would have been flowing in that lamp. Now let's look at question 2. So that was question 1. Question 2 says, a battery circulates charge around the circuit for 30 seconds. If the current in the circuit is 5 amperes, what quantity of charge passes through the battery? So in question 1, we were given the quantity of charge flowing and the time for which this charge was flowing, and we're asked to calculate the current. In question 2, we're now given the time and the current and now asked to find the charge. So once again, we'll begin by writing on the information that we have using the usual symbols. And we use one of our equations to find what we want to find, which in this case is the charge. So the time you're given here, so the time taken T is given as 30 seconds. So in this case, we're given the time in seconds, so therefore there's no need to do any conversion. We're told that the charge, well, not the charge rather, but the current I. So the current I is equal to 5 amperes. And we want to find the charge Q. Alright? So of course you know that the equation relating current, charge and time is I equals Q over T, from which of course we get that Q is equal to IT. So the charge is equal to the current times the time, and of course this comes from the equation I equals Q over T. And therefore this gives us that Q is equal to 5 amperes times 30 seconds, which gives us 150 coulombs, right? So the SI unit of the ampere, or the SI unit of current rather, is the ampere, and the SI unit of time is the second. And when, of course, when you multiply current by time, you get charge, the SI unit of which is the coulomb. And of course, as we've seen in previous videos, the coulomb is essentially equivalent to the ampere second, right? If we look at this equation, current is equal to charge divided by time. So to get the unit of current, we divide the coulomb by the second. And of course, we have already established in a previous video that the ampere is equivalent to the coulomb per second. So 1 ampere would be equivalent to 1 coulomb of charge flowing for a time of 1 second. So that was question 2. Now let's look at question let's look at question 3. In order to look at question 3, I need to make some space. All right, question 3. Now, question 3 says a current of 10 amperes flowing through an electric heater for an hour converts 8.64, this is megajoules, the prefix M here stands for megajoules, a million joules, right? Converts 8.64 megajoules of electrical energy into heat energy. Calculate A, the total charge circulated through the heater, and B, the PD across the heater. So I'll read the question once again. A current of 10 amperes, and of course, as I read through this time, I will write down information that we are given using their respective symbols. So we have a current of 10 amperes. So this is question 3. So the current I, so this time I'll just use the symbols. The current I is equal to 10 amperes. And we're told that this current flows through an electric heater for an hour, right? Of course, the hour represents a period of time. So therefore, we can say that T is equal to 1 hour. But of course, we must recall that the SI unit of time is the second and not the minute, not the hour. And therefore, if we're given the time in minutes or hours, we must therefore convert to seconds. So we know that 60 minutes equals 1 hour, and of course 60 seconds equals 1 minute. So therefore this is equal to 60 by 60, which gives us 3,600 seconds. So 1 hour is equivalent to 3,600 seconds. So let's continue. So it flows, current flows for an hour, and it converts 8.64 megajoules of electrical energy into heat energy. We'll represent that energy conversion using the symbol W. So the energy converted, W, is equal to 8.64 megajoules. Now, as I mentioned before, the symbol M represents the prefix mega, which is basically 1 million or 10 to the 6. So this is the same thing as 8.64 times 10 to the 6 joules. So this is the amount of electrical energy which would have been converted to heat energy by this lamp. In part A of the question, they want us to find the total charge circulated through the circuit. So in part A, we want to find the charge Q. And of course, we'll write down the formula that we'll use to calculate the charge, and of course, we'll proceed to calculating the charge. So far, the equation which relates current, charge, and time is given by Q equals IT. So Q is equal to IT, and since we have the current I, which is 10 amperes, and the time of 3,600 seconds, we can proceed to calculating the charge. So this gives us 10 amperes times 3,600 seconds, which of course gives us 36,000 coulombs. So 36,000 coulombs, or if you prefer to write it in standard form, there's the same thing as 3.6 times 10 to the 4 coulombs. Right? So once again, we're multiplying current in amperes by time in seconds, and that gives us charge in coulombs. So that is the charge there in coulombs. Now let's look at part B. In part B of the question, we're asked now to find the PD across the heater. Now, in previous video, we would have looked at the definition of potential difference, and we have basically said that the potential difference across a component, essentially, we'd have defined potential difference in terms of the energy converted from electrical energy to other forms per coulomb of charge flowing through the particular device. So we basically say that if W is the amount of energy converted from electrical energy to other forms, when a quantity of charge Q flows, then the potential difference V across that device is given by V equals W over Q. So once again, if W joules of electrical energy is converted to other forms of energy, when a quantity of charge Q flows within a particular device or flows through a particular device or between 2 points in a circuit, then it means that the potential difference across that device or between those 2 points in the circuit is given by the equation V equals W over Q. And having written down the equation, we can then proceed to substituting the values and then finding the potential difference. So W is 8.64 times 10 to the 6 joules. So this gives us 8.64 rather. So 8.64 times 10 to the 6 joules, That is divided by charge of 3.6 times 10 to the 4 coulombs. So 3.6 times 10 to the 4 coulombs. And we go to our calculator and we work that out. There is one. So we have 8.64 divided by 3.6. That gives us 2.4. So we can say this is equal to 2.4. This will be times 10 to the 2 volts. Right? So 2.4 times 10 to the 2 volts, or simply 240 volts. So therefore, the PD across this heater would be 2.4 times 10 to the 2 volts, or 240 volts. So basically what this means is that while this lamp is a part of that electric circuit, if we were to take a voltmeter and connect it across this lamp, we're supposed to get a reading in the region of 240 volts. So that was question 3. Now let's proceed to question 4. Now question 4 says a battery circulates 60 coulombs of charge around the circuit. A, if the PD across a lamp in the circuit is 12 volts, how much energy is converted into heat and light by the lamp? And B, if the charge is circulated at a constant rate for 20 seconds, what is the current in the circuit during this time? So let's read the question again, and this time we'll write down the information that we're given in the question. So the first piece of information that we're given is this 60 coulombs of charge, and therefore using our symbol for charge, we can say the charge Q is equal to 60 coulombs. Now, before I go any further, I must mention that when it comes to charge and the coulomb, 1 coulomb of charge is a massive quantity of charge, and so therefore, in practical situations, you will never have to deal with such massive quantities of charge. But of course, it's just a question, and the questions don't necessarily have to be very, very realistic, right? So a battery circulates 60 coulombs of charge around the circuit. So Q equals 60 coulombs. Part A of the question asks, so let's look at part A. Part A says if the PD across the lamp in the circuit is 12 volts. So the PD, or the potential difference, or the voltage, as you may often refer to it as, symbol V, is given by 12 volts. And in this part of the question, they want us to calculate the energy, that is, how much energy is converted into heat and light by the lamp. Now, as I mentioned before, when I speak about the PD across the device, essentially we're talking about the amount of electrical energy which has been converted to other forms of energy per coulomb of charge flowing through that device, right? So using the formula, of course, which relates potential difference V, charge Q, and energy W, the formula is V equals W over Q. And from this equation, we simply get that W is equal to QV. So using this equation, we can therefore calculate how much energy has been converted from electrical energy to light and heat, mainly light and heat by the lamp, right? So this gives us 60 coulombs times 12 volts, 6 12s, that's 72. So this gives us 720 joules. So this means that this lamp would have converted 720 joules of electrical energy into mainly light and heat by this, into mainly light and heat. All right? Heat, rather, not heat. All right? No. So let's move on to part B of the question. So part B of the question. Now part B goes on to say, if the charge is circulated at a constant rate for 20 seconds, what is the current in the circuit during this time? So we still have the charge from before, so we can write down Q is equal to 60 coulombs. Now for part B, we're given the time. So the time for which a charge is circulating is 20 seconds. So therefore the time T equals 20 seconds, and what we want to find now, we're asked to find, is the current in the circuit. So once again, we use equation which relates current, charge, and time. That equation is I equals Q over T. So this gives us 60 coulombs divided by 20 seconds. Of course, this gives us 3 amperes. So therefore, the current which will basically flow in the circuit during this time is 3 amperes. All right. Now, we are basically told that the charge is flowing at a constant rate for 20 seconds, which basically means that every 20 seconds, the same quantity of charge would flow. So or every second, then we could say every second the same quantity of charge would flow, and the charge is essentially flowing for a time of 20 seconds. So during this time, of course, it means that the current we normally would consider to be a steady current, right? Steady current basically means that the same quantity of charge is flowing per unit time or per second. So the steady current basically works out to be 3 amperes. So in this short video, we're able to look at equations relating the current, charge, and time. In particular, I equals Q over T, or Q equals IT. We're also able to use equation relating the potential difference, energy converted, as well as the charge flowing, and we're able to use those equations to do a few calculations.